Okay, so let's talk about UV vis spectroscopy as it pertains to what you're going to be doing for your spectrometer build project. The first thing I want to talk about are just sort of basic ideas and the components that go into an absorption spectrometer. Now, this image that we're shown here is for a dual beam spectrophotometer. It is this is a relatively complicated layout. It's not something that we're expecting you to build, but I wanted to point out that even with something like this, there are a few main components that go into the spectrometer. So there's basically four parts. The first part is the light source, and we will talk about each of these individually as we go through. Here there's a lamp that an ultraviolet lamp and a visible lamp. That then goes to with the second part, which is a monochromator. Monochromator allows us to select one wavelength. So in some form, there's a way of taking a white light spectrum and separating it into its components. The next part is the sample. Again, this is dual beam. Some of our spectrometers are not dual beam. You're going to see a couple of those on the next few slides here. And then lastly, we have detector. So our four components of a spectrometer are the light source, monochromator, sample compartment of some sort, and a detector. There are a few different types of detectors that we're going to talk about as well. So what you are going to have available to you are going to be just a few things. You're going to have a transmission grating. You're going to have an LED flashlight, two cuvettes, because we're going to be building a dual beam spectrometer, and a couple of mirrors. Okay, so that's it. You're also going to have available some cardboard boxes, tape, and other things like that. We'll have scissors in the lab for you for cutting. So the idea is to take these components that we're giving you in your spectrometer kit and building a box to put those components into to make a spectrometer, and you will supply the detector, which should be a smartphone. If you don't have a smartphone that will work with this, let me know, and I have a couple of spares laying around, so we'll make it work. So let's take a look at the light sources here in the spectrometer. So in a typical spectrometer, you'll usually see two different types of light sources in the one box. A light that covers the UV region, which is deuterium lamp, and then we have a tungsten lamp, which covers the visible region. Now there are a few spectrometers that are able to use a xenon light source, and that covers the full UV invisible region of the electromagnetic spectrum. But this is kind of the two lamps that are commonly found in your higher end instruments, although that may be changing too. This is what we have in the Carry UV vis in the lab. Okay, so you notice that the deuterium lamp, again, that covers the UV range, which extends from about 200 nanometers to almost 400 nanometers. And then the tungsten lamp covers the visible range from about 300-ish nanometers on out to longer wavelengths, over 1,000 nanometers. Now your little flashlight that you're going to have this is the only light source you're going to use. Is not going to cover the the ultraviolet portion of the electromagnetic spectrum, and that's totally fine. We're only concerned about the visible portion of the spectrum. So one of the things you'll see, you may have seen if you're buying light bulbs and things like that, is a different color temperature for a light bulb. These color temperatures refer to the temperature that of a black body radiator, which would give off a certain color. So it's related to black body radiation. For a sort of warm color temperature, we would have a spectrum that looks like this red curve here, color temperature of about 3000 Kelvin. And you'll notice that the majority of the light is emitted at the red edge of the spectrum, so that would be the warmer colors. A cool LED, cool color temperature generally has a range of 4000 to 4500 Kelvin, but you can see by looking at this 5000 Kelvin where we're sort of headed, the spectrum shifts greater intensity towards the blue end of the electromagnetic spectrum, and so the colors appear more cool to our eye. And then we were able to get a full spectrum as we increase the color temperature. So around 6000 Kelvin, this is typically referred to as the full spectrum for our light sources. Now, I don't know exactly what the spectrum looks like for your LED, but that is something you could measure. Okay. So then that covers our light sources. The next thing that we said, the next component that was important in a UV vis is the grating or monochromator. So a monochromator is going to contain a grating. That's what's going to be used to separate out the different wavelengths of light in a white light source, or at least approximating a white light source. And so what we have in this image here is a particular type of monochromator where white light would enter through this entrance slit, bounce off of a concave mirror that's going to focus that light onto a reflective grating or reflection grating. That grating is going to separate out the light. We're going to talk a little bit more about how that works on the next slide. But then that light is reflected onto another concave mirror, which then focuses the light back down onto an exit slit. And different wavelengths, depending on the angle of the reflection grating, are going to be able to exit through this slit. So basically, different wavelengths of light are diffracted at different angles, and that angle of the grating is how we select which wavelength is leaving the monochromator through the exit slit. When you're using the UV vis in the lab, the carry instrument, you're going to hear some noises as the instrument is running, and part of that is the rotating of the grating. So when you're running your samples, take a listen and see if you can hear that happening. Okay, so let's take a look in a little bit more detail how gratings work. Again, we're separating light into its individual components, and the way that we do that is different wavelengths are diffracted at different angles, and every grating, there are lots of different types of gratings, but one of the sort of ones that was initially utilized were these types with grooves. Okay, so these grooves were carved into a surface in some way. Those grooves on the grating affect the way that light is reflected off of the grating. And what that then does is it affects the amplitude and phase of the incident radiation, which causes some form of interference. It could be a constructive interference or a destructive interference. So if you haven't seen the grating equation already, you will see that in your course that corresponds with the lab that you're in now. So we have in a grating a series of grooves that are separated by a distance that should say A. And we have a couple of angles that are important here. Theta sub I is the incident light angle onto the grating, so relative to the normal. So here's normal to the grating, so that's perpendicular to the grating. And so the angle that the light comes in is theta sub I. And then we have the angle at which the light is reflected, and that's theta sub M. And we have diffraction order to worry about as well. Usually we're thinking about first order diffraction. There are other orders, but we're not going to really get into that. So essentially, if you have incident light that is completely perpendicular to the face of the grating, then this is your grating equation, which says that the angle at which the light is reflected is dependent on the wavelength of that light. Okay, it also is dependent on the groove spacing, but in any case, we're able to separate out the wavelengths of light because the wavelength is dependent on the angle that is incident on the grating. When the light isn't perpendicular, isn't normal to the grating surface, then we have a couple of different equations here. So we have an equation when we're using a reflection or a reflective type grating. So that's when the light comes in, a different color light comes in, and then is reflected off the surface. So usually there is a mirror-like material on the surface of the grating. And the other type of grating that we have is a transmission grating. So that means the light is essentially going through the grating in some way. That's the type of grating that you're going to be using in your spectrometer. So there's slightly different equations for those. And these also take into account the angle at which the light is either entering or reflecting off of the grating itself, the incident radiation, and the reflected angle. So I mentioned that the separation of wavelengths occurs because of constructive and destructive interference. So what does that mean? So if we have a light of a particular wavelength, it can interact in a constructive way or a destructive way. Okay, so at a particular angle, a certain wavelength is going to be bright, and everything else is going to be eliminated, essentially, or nearly eliminated. So the wavelength that is bright because of constructive interference. So if we have light of a particular wavelength with this amplitude and phase, and it interacts with another wave of the same amplitude and phase, or at least the same phase, then we end up with this result here: greater amplitude, same phase. If the two waves are partially out of phase, when these waves interact, you end up with a result in which the amplitude isn't as great as our first example here. If the waves are completely out of phase, then they undergo destructive interference and then basically completely eliminate each other. Okay. That is a very quick overview, but that's sort of not like the goal here of this little video. So in any case, let's move on. Let's think about the detectors. So there's three common types of detectors: a photomultiplier tube, that's what's shown here, a photodiode array, and a charge coupled device, or CCD. Okay, we're going to talk about these just in some small detail here. The one here in this previous slide here is a side-on. So how does a photomultiplier tube work? So essentially, what happens is light or a photon enters the photomultiplier tube and strikes a photocathode. From there, that photocathode ejects an electron, which is then attracted to an anode. And there's a whole series of these anodes that make up a dinode chain. And every time an electron hits an anode on that dinode chain, more electrons are ejected. So this should say 10 to the 6. So when we have one photon that enters into the photomultiplier tube, at the detection anode, we basically will have 10 to the 6th electrons that we can use to create a signal. There's a couple of different designs for these photomultiplier tubes. There's a linear, head-on photomultiplier, and then a side-on. I wonder how that will show up. Anyway, so the next thing we have is a photodiode array. This is what we have in the UV vis that's on the cart. So that's the HP 8453 instrument. And we're going to talk a little bit more about that one. So the nice thing about a photodiode array is that it can record an entire spectrum in just a fraction of a second. And so we can think about basically the photodiode array acting as essentially digital photographic paper. So you take a picture. If you use film, you click the button and you get the picture. That's essentially what's happening with the photodiode array. So when light hits the photodiode array, it generates free electrons and holes, and the photodiode array uses p-n junctions. So the electrons migrate to the p region, the holes migrate to the n region, and then this discharges the capacitor. The way we interpret that is the amount of current that's needed to recharge the capacitor is measured, and that's going to correspond to the intensity of a particular wavelength, and that lets us build the spectrum. So I should say a linear array of diodes. So each photodiode in this linear array is going to be able to interpret a certain wavelength. And so it's a lot of very small diodes arranged very closely together. Okay. A charge-coupled device, or a CCD, is basically a two-dimensional photodiode array. It is more sensitive than a photomultiplier tube. Again, we have light hits the CCD, it's absorbed and injects an electron. The hole migrates to the n-doped substrate, and the electron migrates to the p-doped substrate. And then we collect light for a certain amount of time and then figure out how much charge is required to recharge the capacitor. The nice thing about CCDs is that you could, because we have a two-dimensional surface, you could collect a spectrum at the top and you could collect a spectrum at the bottom. And a lot of times when people are using spectroscopies where you take two spectra at the same time, they're going to do a subtraction or an addition or something like that, some sort of mathematical manipulation. But this allows the light source to be consistent when those two spectra are collected. This is just a couple of pictures of what a smartphone looks like if you were to take it apart, the camera portion. The colorful thing here is a CCD. This is your typical smartphone camera. This one is a periscope style, has two different detectors, so there's one here and there's another here. It's kind of interesting. Alright, so now let's take a look at some specific UV vis spectrometer instrument design. So this is a picture of a Spectronic 20. It's an older UV vis. Excuse me. You can tell that it's older for a number of reasons. Well, it just looks older, but also has an analog display instead of a digital display. That's a key indicator there. These were made up until relatively recently, and they are workhorses. They're really good. They had so few parts and so few moving parts that they rarely broke. They were used a lot in general chemistry labs and places like that. And fun information here. There was a Spectronic 20 in the movie Back to the Future. Okay, and let's see. Anyway, so if we take off the cover of this Spectronic 20, we would open it up and find something like this. So you can still see our digital display, or excuse me, analog display. The top numbers are going to show the percent transmittance, and the bottom is the conversion to absorption units. And the way this works is, notice there are two. Let's go back to our first image here. This is a sample compartment. Okay, this knob allows us to select a particular wavelength, so that's going to change the angle of the grating. And then these other knobs are for zeroing out the instrument and removing background and things like that. Okay, so once inside the instrument, we have a light source. That light goes to the grating, which then is reflection grating, which then reflects the light back through the sample compartment, and then to the detector, which is on the other end. So the light path is sort of like this. So it makes an angle, almost like a triangle, I guess, if that's what my 4-year-old would say. It makes a triangle. But so it's a very simple design, very few moving parts, very few electronics. This is why these stuck around for so long. And then just here in this other image of the inside of the spectrometer, you can see this colorful part. That is the grating. So if you were looking inside the spectrometer, you would be able to actually see that. Okay. So after the Spectronic 20, this is a very simple design. Measures one wavelength at a time, one beam path. Okay, single beam instrument. We then can sort of go one step more advanced, I guess, maybe a couple of steps more advanced. And this is the HP8453 that I had mentioned previously. This is the instrument, the UV-Vis instrument that we have on the cart in the lab. So in this instrument, we have a light source, which is located on the back. The sample compartment is in here. It's actually not covered, and that's totally fine. There's not a lot of stray light that can get to the photomultiplier tube. So you can actually just leave that open, uncovered. Sample goes in here between these two compartments, two boxes, and then the detection is on this side. Okay, so let's look at the instrument design. I like this figure because you can actually see where all of the components are inside the instrument. So I mentioned the light sources. There's actually two lights in this instrument, the tungsten lamp and the deuterium lamp for the visible and then UV-Vis. There is a shutter. It opens and closes to allow light to pass or not to pass. A focusing lens focuses the light onto the sample. And then another lens to focus the light through a slit. Then to a grating. And from the grating, then the light is reflected onto the photodiode array. Okay. So another simple design, light source, sample, and then grating, and then detector. Okay. And then, so here's our Spectronic 20 layout. Light source, to a mirror, to a sample. Oh, I'm sorry, this is not a Spectronic 20 layout. I apologize. This should be the HP 8453 layout. Let's change this here. HP 8453 layout, because it has the photodiode array. So we go light source to a mirror, sample, mirror to the polychromator, the grating, and then to a photodiode array. This is maybe not exactly the 8453, but it is a photodiode array layout, okay? But the key thing here to note is we go from light to sample to grating to detector, okay? That may be an option for you when you are building your dual beam spectrometer with your smartphone. We then can look at more complicated dual beam spectrometers. So this is a Perkin-Elmer instrument. I don't remember the model number, but it is a dual beam. This is the sample compartment with a reference and the sample, and then the associated layout with that. So in this, we're going to have our light source. Let's do this. Light source, then to the monochromator, then to the samples, and then to the detector. So this layout's a little bit different. This is light, then we're going to put grating, then sample, then detector. In this style, the grating and the sample are swapped compared to the previous one we just looked at. So that might be something to think about. What is going to be the thing that works, the layout that works best for your smartphone spectrometer? So I mentioned that there is a paper that shows you exactly how to build a dual beam spectrophotometer. This is that paper. This is the reference for that. Adam Smith and co-workers. So you can see they have a 3D printed box or base and a smartphone holder. The smartphone goes into the holder. That then sits snugly on the base. It's mounted there. Your sample and reference go into these cuvette holders, and then the light source comes in through this base. I believe there's a mirror in here as well. So if we look at it from the top, we have the light go into the samples, to a mirror, through a grating, and then to the detector, which is the smartphone. Please take a look at this paper and the associated supplemental information. That's definitely going to help you figure out at least a starting point for building your spectrometer. So your task in building your spectrometer is to use the provided materials. I talked about all of those. Try not to spend any money on this. If you need something, ask first because I might have it somewhere. Using things that you may normally be thrown away is encouraged. Common household items. The idea, think about, if you were to take your design back to your high school or something like that, could they easily implement this on their limited budget? Okay, think about how to make that work. You are going to use your spectrometer to collect a spectrum, at least one spectrum of a solution. And when you collect that spectrum, it isn't going to look like, absorption versus wavelength, and look like that. It's going to actually look like what we see when we reflect light off the grating, okay? So we're going to need to convert that to an actual absorption spectrum, and we're going to use the software called ImageJ. And this is available for free off the internet. It's reliable, it's good, and I think that it will work on both Mac and PC. So, and what does a successful spectrometer look like? Well, so make sure you're taking notes, and what does a successful student do? Take notes along the process. There are going to be a few assignments to keep you honest in taking notes. The assignments will be associated with each build day, so there will be one due after each build day, in lab build day. They're very metacognitive in the questioning. Like what materials have you gathered, what references have you used, things like that. Work throughout the semester until the final due date, okay? And don't wait till the last minute. That's why we have these in-lab build days, because if you wait to the last minute, this is not going to be fun, okay? Please ask questions. Like, we want you to come up with a spectrometer that works. And I think that, it's doable. It is very challenging, but it's doable. Feel free to share ideas with each other, but don't overstep your boundaries there, okay? Your work needs to be your own. Everyone needs to be working individually. Don't build parts for another person, for instance. There are points, 50 points allotted for a working spectrometer. So if you collect a spectrum that looks like it's supposed to look, that will give you some nice credit. And then the final project, the final work that you turn in is either going to be a video or a document on the build process and the way the spectrometer works. There's more details of that on Carmen.